A positive point charge Q is surrounded by an uncharged hollow spherical conductor that has an inner radius of R1 and an outer radius of R2. So, for part A, what total charge exists on the inner surface and the outer surface of the conductor? So the conductor itself is uncharged, which means that the total charge of the entire conductor is going to be 0. But since charges are free to move in a conductor, and there's a positive charge at the center, that means a whole lot of negative charge is going to be attracted toward that positive charge. So all along that inner surface of the conductor, there's going to be negative charges, which I'm drawing here, just representing them by negative signs. The total of all those negative signs, of all the negative charges, will exactly equal to the magnitude of that charge in the middle. So on the inner surface of the conductor, the total charge altogether is equal to negative Q. So what about on the outer surface? Well, since the whole conductor is uncharged and charges are free to move, those negative charges must have come from a place that leaves a positive charge. So on the outer surface, there's going to be a net positive charge, which I'm going to represent by plus signs all around the conductor. And all those positive charges add up to a total of positive Q. So with the inner surface having a total charge of negative Q and the outer surface having a charge of positive Q, the total on the conductor altogether is equal to 0, which should make sense because it says the conductor is uncharged. For part B, draw the electric field lines on the figure. So we know electric field lines come out of positive charges and go into negative charges. So I can start by drawing some field lines from the positive charge at the center to the negative charges on the inner shell of the conductor. And put the electric field line arrows in the direction they're going. Now, one of the properties of conductors is that there is no electric field inside a conductor. So you should only have the electric field lines going up to the inner surface of the conductor. Then inside the actual conductor itself, in this whole gray area, you should not have any electric field lines. But then on the outside of the conductor, the field lines will basically kind of pick up where they left off. So it'll look something like this. For part C, sketch a graph of the electric field as a function of the distance r from the point charge. So you can see from the diagram that the electric field is the strongest closest to this charge, and it gets a little bit weaker because the lines are further apart as you get toward R1. Then between R1 and R2 the electric field was 0, and then outside of R2 it goes back to having electric field, it's just weaker than before. So what it will look like on the graph is it starts out kind of high and then it falls, but at the point where it reaches R1 it immediately drops to 0, where it stays there until it gets to R2, and then it just kind of picks up where it left off, continuing like that. And for part D, sketch a graph of the electric potential as a function of the distance. We know that's an inverse function, but we also know that since the electric field is 0 inside the conductor in that gray area, that's where the potential remains constant. So this graph is going to look like similar to the E versus R graph. It's going to start by kind of dipping downward, but when it gets to R1, it's going to be a horizontal line, not at 0, and then it starts dropping off outside of that. So that's the potential graph. That's the graph of potential versus distance.